Hello everyone, I am Mudita Girk. I am pursuing Masters in Business Analytics from University of North Texas. And today I'm here to present my final project in deep learning with big data. So I'll walk you through the project with some basic terminology in case that you have never heard about those terms or if you have never worked with them, it will be easier for you to understand my project. So what's AI? I'm pretty sure everyone must be thinking about it. And since it's rolling currently nowadays, so I'm sure that most of you are familiar with the term AI as it has been a major focus, especially in those Hollywood movies like The Matrix, Terminator, Interstellar. Although Hollywood films and science fiction novels portray AI as human-like robots taking over the planet, the actual evolution of AI technologies is not even that smart or that frightening. Instead, AI is grown to offer many different benefits across industries like healthcare, retail, manufacturing. You can see the self-driving cars, Tesla. So what's AI? You can see this diagram. AI has different subsets: machine learning, deep learning, NLP, speech recognition, robotics, vision. So we are focusing on deep learning in this project, but there are subtypes of it. So the evolution of AI, it's it's recently started creating an hype, but it has been from, you can see here, it has been here since 1950s. And you can see the deep learning, how it has been in the breakthrough and everything. So deep learning recently started getting famous, and you will soon know why it started getting famous. But just remember this, that AI has been here from a long time. It has not started recently, but the hype and the awareness has started creating recently. So what is actually the difference between AI, machine learning, and deep learning? So in short, the AI is basically nothing super type of both machine learning and deep learning, but every one of them has different differences between them, just the minute differences. So in machine learning, it's loosely interpreted. I mean, people interpret it differently. It is basically a computer system with the ability to learn. And the intention of machine learning is to enable machines to learn by themselves by providing the data and making the accurate predictions. Whereas deep learning is the next evolution of machine learning. It's a subtype of machine learning where it is mimicking the human brain. Just like how our brain works, deep learning also works in the same way. So these are the minute differences between the three of them. So I told you I'll get back to this question, that why deep learning is so popular these days. So you can see this graph where the amount of data is increasing and the performance is also increasing. So in the previous algorithms which have been developed before the deep learning, they become somewhat constant with the amount of data. There is no significant change in the performance. Whereas in deep learning, you can see the change. It's growing, the performance. Hence, this is one of the reasons why deep learning is so famous in researchers and in different companies, because the data is now growing huge. Since we have gone digital, the data is also growing. The second can be the second reason that deep learning is so popular is because it creates its own features. If you have worked on the previous algorithms, or if you have knowledge about the previous algorithms, you must have seen that you need to input the features. You need to specify which one is our target, which one, you check the correlation between those variables and everything. But in deep learning, you don't need to do all of that. It can create its own features. It can check everything by itself. And the third reason is because it creates a large scale neural networks that allow the computer to learn and think by itself without the need of direct human intervention. So you don't need to interfere while working, just specify what you want and deep learning will produce it for you. Isn't that good enough? I mean, just little bit amount of effort and deep learning will do wonders for you. So now this is deep learning architecture. Even in deep learning, it has different types, just like any other machine learning or NLP. So deep learning has supervised and unsupervised. So supervised algorithms where you need to specify what is our goal, what is our input, and you need to specify steps for that. Whereas in unsupervised, there is no fixed output or goal. You just input different features and you expect an output. You want to see what type of different patterns can be produced from the unsupervised. So in supervised, there is convolution neural network, recurrent, and in unsupervised, it is self-organizing maps, autoencoders. So we are dealing with the supervised part in our project, which is CNN, convolutional neural network, which I will explain you later how it works and everything. So in general, how deep learning works. So the main motive of deep learning is to simulate human-like decision making because it has been developed on the human making mimicking behavior. So neurons in the brain pass the signals to perform the actions. Similarly, in AI, neurons connect in a neural network to perform clustering, classification, regression, and different other stuff. Neural network sorts the unlabeled data according to the similarities of the data. So even if you have a data which is not labeled, it can perform uh, processes and they can sort the data with the similarities of what type of data it is. For example, if you have a data set which has cats, dogs, puppies, everything, but those are not labeled. So a neural network will sort them on the basis of the features of the images. So it will put puppies in one label, dogs in one label, cats in one label, something like that. So neurons are made up of three layers: input, hidden, and output layer. So as you can understand from input layer is the one where you receive the input from the observations. Hidden layers are the layers where you perform feature extraction and transformation. And output layer, as you can understand, you get output from it. So this slide talks about how a simple neural network is supposed to be and how a deep learning neural network is supposed to be. So for example, in simple neural network, there is one input layer, one hidden layer, and one output layer. So you can understand from the term simple, it's very simple. So in deep learning neural networks, deep means the number of layers it has between input and output. This is the meaning of deep learning, that it has number of hidden layers in between them. Whereas neural network only means one input layer, one hidden layer, and one output layer. It can be n number of hidden layers, but then it will be called deep learning neural network. I hope you guys understood the difference between simple neural network and deep learning neural network. It's just the number of hidden layers between both the architectures. So activation functions. Activation functions define the output of input or set of inputs. In other terms, it defines node of the output that is given in inputs. They basically decide to deactivate neurons or activate them to get the desired output. They also perform a non-linear transformation on the input to get better results on a complex neural network. So activation functions are really important in our building the neural networks. Because, for example, if you did an input of 5 and 10, and you are summing those two numbers in the hidden layer, and you expected an output to be 15, but you saw the output is coming out to be 11. So you perform activation functions to get the desired output. You make some transformations in it, and you understand why it is not giving you an output as 15 and why is it giving you as 11. Why is there an error between those outputs? So activation function is really, really important. So these are some common activation functions: sigmoid, tanh, relu, leaky relu. So all these have different mathematical concepts behind them, which I will not go in depth, but you can study the statistics of all the activation functions. In our project, we are I'm using relu, which is this third one. So relu's full form is rectified linear activation function, and it's a piecewise linear function that will output the input directly if it is positive. Otherwise, the output will be zero. So if it is giving us a positive result, it will do the transformation. Otherwise, it will give you an output as zero, as you can see from the graph. So same thing. So why ReLU is more important, or why are we using ReLU in our data set or project? So ReLU is used because it trains much faster due to its linear non-saturating form. It's easier to implement, and it accelerates the conversions of stochastic gradient descent. So stochastic gradient descent is when there is a learning rate and you want it to reach the desired output. So it accelerates that conversions for you. Hence, activation ReLU is a better choice than the other ones. ReLU is more expressive, and it is less expensive operation. So you also need to think about the cost when doing the project. If we'll use a activation function which is more expensive, but if it is giving you the same results, the cost is going up for no reason. So you need to focus on that also. Another function is softmax function. As you can see from the graph here, it gives you an input. This is our normal neural network. So in the hidden layer, there is a logits layer. For example, the input was Apple. So it will check, is Apple yes or no? If it is yes, then it will give it in the next layer an output. But if it is not, then it will not proceed. So softmax function is basically used as the final layer, so that here is the output layer. So once it gives Apple yes or no, it can produce that this particular label is generating apples. So hence it is used as the last layer. So the function squeezes the outputs between 0 and 1. So whatever data it is coming here, it will squeeze them into 0 or 1. So 0 is whether that apple is yes or no. Yes is 1, no is 0. And softmax function is helpful when we have probability, or when we have classes, when we want to predict whether this belongs to that label or not. So there is a probability going on. So it is useful when we need to find an output in a particular class. And next slide is why GPU matters in deep learning. So GPU and CPU, there are two terms. And GPUs are optimized for training AI and deep learning models, as they can process multiple computations simultaneously. So deep learning is famous because you can run parallel computations, unlike the other machine learning algorithms. So GPU helps in boosting that performance. If you can't run it parallelly, then there is no point in doing the deep learning. So as you can see in the diagram here, this is a snapshot from the neural network. So it is taking 734 seconds if I'm not running with GPU. And with GPU, it's only taking 27 seconds. So can you see the difference? And obviously, if you're training data with huge amounts of data, and as it is mentioned in deep learning, you would want the model to be trained easily and more efficiently. So it's always better to have GPU rather than not having GPU. So with GPU, the running time is 27.1 times faster than without the GPU. So TensorFlow and Keras, everyone must have heard about it. So when to use TensorFlow and when to use Keras? In my project, I have used TensorFlow. So TensorFlow is easy model building. It gives you robust ML production, and it is used for powerful experimentation for research. So TensorFlow gives you flexibility to control features which we want in our project. TensorFlow offers multiple level of abstraction, and it also lets you train, deploy your model easily. No matter what language or platform you're using, TensorFlow makes your life easier. Keras. Keras is another library which can be used for deep learning. So it allows easy and fast prototyping. It is user friendly. It gives you easy to use access, easy to extend, modular and composable. So you can use either of them, but in our project, we have used TensorFlow. So what is CNN now? So CNN is the convolution layer. Each neuron is connected to a subset of input neurons, and it corresponds to the pixel located next to each other. So as you can see here, it is corresponding to the pixel here, it is corresponding to the pixel here, and so on. So I can show you how they work, the feature mapping works through this diagram. So this is the box, and it took the highest feature over here. From here, 8, from here, 9, and from here, it's taking 7. So this is how the max pooling happens. It takes the highest feature and puts into the different mapping. So optimizing images. As you can see, the post-processing feature, after processing it, it is enhancing the color, curves, and details. In the next, it is giving you an illumination. And this is giving you warmness. So the big question is when to use deep learning or not over others. Deep learning is a very technical field, and it requires a lot of data. So if you have a small data size, try to avoid deep learning and try to use other machine learning algorithms. Deep learning also requires a high-end infrastructure to train in reasonable time. Deep learning also requires a lack of domain understanding for feature introspection. If you don't have that domain knowledge, then you will not be able to interpret the results properly. So our project, first we are doing MNIST dataset. So it is a handwritten digits dataset with 60,000 examples in the training set and 10,000 in test set. It is a subset of a larger set from NIST, and these digits have been size normalized and centered in a fixed size image. So these are the images in the dataset. As you can see, those are handwritten, fixed, properly placed in the center. The another data is CIFAR-10. that data consists of 60,000 images, which is 32 by 32 color images in 10 classes, with 60,000 images per class. Then the dataset is divided into 5 training batches, which has 10,000 images per batch, and it includes 1 test batch and 1 metadata. So as you can see here, it has different images, colored images, and it has these 10 labels for those images. So the objective of the project is to deal with the classification problem and to build, train, and test a classification model using TensorFlow, which can classify images in a right label. First, we will load the dataset. Since we are using Google Cloud Platform, I have already uploaded the data in the remote server. Then we will perform one hot encoding on it. So since the data is already in pixels value, so one hot encoding you can see here as the example. It has 1, 2, 3, 4 red, blue, green. And then if you need to convert them, you need to put it like this. So for the first color red, everything is 1, 0, 0. For blue, it is 1 here as 0, 2, 3 as 2. Here we have blue, so it's 1. Green we have, so 0. Blue again, so we have 1. This is called one hot encoding. Then we will do the data pre-processing. So since our data was in different files, we try to include all the files in one by using unpickle method. Pickling converts Python objects into stream of characters, and it is easier to perform stuff like that. So we performed data visualization, which I have not shown in my slides because the data was clearly, the images were very small as compared to the modern photographs. It can be challenging to see what exactly it's represented in some of the images, given the resolution was extremely low. Maybe the resolution is like because of the limited performance of the algorithms, or it could be any reason. So now we are building our CNN model. So the CNN model works in 3 stages. The first stage is to extract the features. Second stage is pooling layer reduces the dimensionality of the image. So small changes that, it does not create a big change on the model, just to prevent overfitting. The third layer is flattening layer. It transforms the model in one dimension and feeds it to the fully connected dense layer. Dense layer means that every node is connected to each other. Hence, it's called dense layer. And then the dense layer performs the prediction of the images. So in our data set, we have 32 by 32 input images with 3 channels, which is RGB, red, green, blue. And since we are working with 10 different categories, we make sure that we apply reshaping to them so that it can convert into these layers. Then that model has a lot of different stuff to include. I'll go back, explain few more slides. So this max pooling is a downsampling filter. It reduces a 2 by 2 matrix of the image to a single pixel with the maximum value of the 2 by 2. That filter aims to conserve the main features of the image while reducing the size. So it has a lot of different stuff which we need to explain in detail. I'll just tell you few points so that you can understand. In the next layer, when this image is converted into a small size here with the same channels, Then it goes to the convolution layer with ReLU. So dropout is a regularization layer in our model. 25% of the nodes in the layer are randomly ignored. This prevents overfitting. ReLU here is the rectifier and it is used to find non-linearity in the data as I explained it before. Then the flatten converts the tensors into 1D vector. And the dense layers are neural ANN. The last layer returns the probability that an image is in each class or not. For example, here, if that image is a bird or a cat or whatever we have in the data set. So first we input this image, converts it into um, this layer, then it reduces the size, then the activation function is given, then again reduces the size, and then it flattens into 1D array and it is fed into the ANN. So the parameters we have used is learning rate, batch size, training steps, and the number of convolution layers. So here the learning rate is updated during the training and it tells you how much amount of weights are needed to be updated. The batch size is a hyperparameter that defines the number of samples to work through before updating the internal model parameters. And we are not using epochs, but epochs is also a hyperparameter which are most commonly used in neural networks. So we have taken 0.001, batch size is 100 and 5,000 and 2 convolution layers. So the results and the conclusion we got is when we were running this data set, we got 62.23% of accuracy. As you can see in the steps, we had 5,000 steps and the accuracy is increasing in each step. So now comparing these new data set with the MNIST data set. So both the data sets have the same number of hyperparameters, but even because of that, we still got accuracy of MNIST as higher and CIFAR-10 as to be lower. So what could be the reason in the gap in performance? So I think since MNIST was dealing with black and white hand digits, it was easier to interpret them as compared to the complex images of cats, birds. So the model complexity was increasing, hence giving out to be the lower accuracy. The another reason could be the MNIST data was normalized, which was not the case with the CIFAR-10. So now improving the CIFAR-10 model. So how can we improve the accuracy? So I performed 3 cases where I tried to change the training steps. And in the third case, I tried to change the learning rate. So when I was trying to change the number of steps, there was not any significant change. But when I changed the learning rate, in only 5,000 steps, I got 69.6% of accuracy, which is pretty good than comparing with the original one, which was 62.23%. So what is the effect of learning rate? So the learning rate hyperparameter controls at what speed the model will learn. So learning rate is very important. If a learning rate is too big, then it will keep oscillating and it will never converge. That means you will never get a good accuracy or optimal accuracy. If a learning rate is very small, it will take a lot of time to learn, and globally, the weights will take longer to train as well, as you can see here. So learning rate is important. As you can see, our learning rate initially was very small, maybe that is one of the reasons that it was not giving us a good accuracy. So the conclusion of the project is, first of all, we developed a CNN model with 62% accuracy, and then we improved it to 69% with the learning rate. And we showed how two different data sets with the same hyperparameters can have gap in accuracy, as both of the data sets are different. And it doesn't mean if everything is same, the result will also be same. Then we fine-tuned our model to provide better number of accuracies. Thank you so much. I hope you understood this.